Hello everyone. So today's lecture will discuss about basic material science. We will quickly review the material science concepts which are required for this course, dynamic behavior of materials. So as you have noticed, in this course we are discussing the things very slowly. So we are going in a very slow pace, but now today I will be little fast because these things are already you have studied in other courses. So what we will do is we will just review. I will just highlight the topics, and probably if you are interested you can study and you can brush up your knowledge with your earlier textbooks of material science, and also you can please feel free to send your queries in the discussion forum. Okay, so before I go to the any topic, so I want to thank my MTech supervisor Professor Anand Subramaniam from IIT Kanpur and Professor Mike Rigsby from North Carolina State University. So these two professors taught me materials science and engineering during my masters and PhD. So some of the materials probably what I will discuss today probably from their influenced by their classes or class notes. So we'll first discuss about the classification of materials. So we know that the common classification of materials is metals and alloys and ceramics, that includes the classes as well, and then polymers and composites, which is a combination of two or more of these three classes: metal, ceramics and polymers. So this is one classification, and the another classification is ductile and brittle, depending on the behavior of the material, mechanical behavior of the material. So that is another classification, and the other one is crystalline and amorphous. So these three classifications you already studied in some of your courses, probably basic material science courses, or even some of these are mostly you studied in your high school standard. We'll just talk about the crystalline and amorphous materials. So if you see here, these atoms are in the left side, it is amorphous. So in these few materials, if you see some in lines, some of the materials may be in some lines, but these are in not all the materials are it is in any particular order, or but here in this case, in the second case, it is we called crystalline material. So why we call it crystalline material? If you see, there are, you can draw some lines here, and they are perfectly aligned. And also the requirement for crystalline material, we should tell that, so distance between these lines are also equal. If this distance is x, and if distance is again x, if this distance is again x. So similarly you can draw lines in this direction as well. So in that way also the periodic order will be maintained. So basically the crystalline material means the periodic arrangement of atoms. Crystallinity actually means the periodic arrangement of atoms, how these atoms are arranged. So this is somehow sometimes we call these are lattice points. If you see this part of of the slide, so if you see that these points are, we let's say call them lattice points. So now I will tell you this, the crystal, you will get this definition in some of the textbooks, not every textbook will discuss these things this way, but the crystal is equal to lattice plus motif. The motif sometimes it is called as basis as well. So what is lattice here is, so lattice is these points. See what I showed you earlier here, these are atoms that you I am sure all of you understood this. So these are atoms, but in here what we are showing is some mathematical points. So these are called, the array of the mathematical points are called lattice. So these points are lattice, and these lattice are, as you can see, that arranged in equal interval. If you see that way, or maybe sometimes you can see this way also, it is an equal interval. So lattice is the only the mathematical points, and the motif is one or multiple atoms. So when you think about some atom, let's say only one atom at one lattice point, so these are the atoms, let's say, on the lattice points. If you want to, if you are now arranging some atoms and then arranging them, keeping them one atom at one lattice point, then this will be called as crystal. So when you write the word lattice, you need to be careful, because lattice only means the mathematical points, but when you write crystal lattice, that will mean that okay, this is something about the lattice of some atoms, and that is correct. So lattice alone does not mean a crystal. And also the unit cell. So this is the unit cell, that is the unit cell is the, this is unit cell. Unit cell, you can define it as a finite representation of an infinite lattice. So the lattice is the arrangement of the atoms. It can be actually infinite, but when you have a unit cell, that means you are having a finite representation how the arrangement of this lattice, and if you translate and this unit cell to here, and then again you can translate this again to here, and then you can represent the entire lattice. So that's why it is, the formal definition is some books will give you that way, the finite representation of infinite lattice. So in this case also we want to tell you that we have 7 crystal systems and 14 Bravais lattices. So Bravais lattices, 7 crystal systems, the most common one is cubic, or let's say hexagonal or tetragonal, and orthorhombic, rhombohedral, monoclinic, triclinic. These are depending on the symmetries, how the atoms are arranged, but we are not going to discuss about the details. But 14 Bravais lattices, if you want to know this, let's say FCC, BCC, SC, that is simple cubic, these all are included in cubic crystal systems. Similarly others you will get more here as well. So that way it has there are 14 Bravais lattices. So what is the difference between crystal systems and the Bravais lattices is that the crystal systems are classified depending on the unit cells, especially unit cell parameters, which we call lattice parameters, A, B, C, or alpha, beta, gamma angles, and the Bravais lattices are from those unit cells. You need to see how the atoms are arranged, and depending on that we can get it is FCC, BCC, or simple cubic. That that FCC has atoms apart from the cube unit cell cube corners. FCC has atoms on the 6 faces as well, and BCC has atoms in the center. So that you already probably know. But then in this slide we will mostly discuss about the another classification. I will write only metal, that includes metal and alloy, and then another one is ceramic. Ceramic will include, as you know, the glasses, and then the third one is, as you know, is polymer. So, and these areas will be common areas, will be we can represent the composite. So very quickly, some important points about these materials are, as you know, metal is mostly ductile material, and then as you know, this classification is based on also the bonding between the atoms. So this has metallic bonding, and also the metals are crystalline nature, what we discussed in the last class, last slide. And then ceramics are mostly, they are brittle, and ceramics are sometimes it can be crystalline, and sometimes it can be amorphous. And the bondings are, as you know, it can be ionic bonding, or it can be even covalent bonding as well. And the polymers are they can be brittle, they can be ductile, even the very ductiles are let us say elastomer, and then it is amorphous with small crystalline groups. So sometimes it is called semi-crystalline with small crystalline regions. So sometimes it is maybe called semi-crystalline, and the bonds are mostly covalent bond for a molecule, and the intermolecular bonds are like secondary bonding, van der Waals bond. So before going to the next slide, so we will again go back to the other slide. So we have left something here. So this is the third one, is the polycrystalline material. Polycrystalline means the same crystalline material. So in this case, in the second diagram, that is a single crystal, right, single crystal in this case. And what is polycrystal? That all of you know that it has multiple crystals in it. So we use the word the crystal, or mostly in mechanical engineering or metallurgy we may use the word grain. So now if you see, this is one grain. So how this grain, the atom alignment are like this, and if you enter into another grain, so the atomic arrangements are little different, in a different orientation. Similarly the third grain, so atomic arrangements are different. So this is that's why this is multiple grain. And as you know that most metallic materials are polycrystalline, because these grain is like in the order of micrometers, like 10 micrometers to 100 micrometers, but sometimes you can make very big grains like for a turbine blades you can make very single crystal turbine blades. So engineers are now so expert, they can make even very big grains in centimeters or meters, and they can also make very small grains like nanometer level. So now the range of grains that is called nanocrystalline material, from nanometer to probably meter you can make grains depending on your expertise in metallurgy, materials engineering. So now one important thing to mention here is that for a metallic material, for a crystalline material, the single crystal is anisotropic. As you know, the definition of anisotropy, I think that means the material properties are different in different directions, and for a polycrystalline material generally we consider it is an isotropic. Why it is isotropic? Because in the single crystal we think that the material properties, let's say elastic properties in this direction, let's say E x, and then let's say in this direction elastic property is Ey, they are different. But in this case, as if you see only one grain, then the material properties will be different in this direction and in that direction. But if you take the average of all the grains, because there will be thousands of grains in a material, because it's only most grains are in micrometer level, so then you can average out the properties. So that means that's why you can get a material which can be considered as isotropic. But there are other cases of anisotropy that you can learn, like orthotropic material, transversely isotropic material, and also if you take a single crystal of other crystal systems like single crystals of cubic crystals, tetragonal crystal, hexagonal, they have all different kind of symmetries and their anisotropy is very different than each other. So different from each other. So they are not isotropic. If you take a single crystal, they are anisotropic, but their anisotropy is different. Cubic crystal is different than tetragonal is different than hexagonal. So now we want to talk about the ductile and brittle. What is the classification we discussed? All of you know about that, but just to remind you the things you learned earlier. So if you draw a stress strain curve, as you know, the very common one general ductile stress strain curve will look like this. This is ductile, and if you draw another one for a brittle material, so this brittle material will fracture it here. So this is for brittle. So there can be material which is somewhat less ductile but not exactly brittle. So now if you do a tension test, let's say you have a specimen, you have, let's say, specimen like this, and you are having a tensile test. So what will happen if it is a brittle material? So the material will break at the middle, at a flat crack, fracture will happen. So this is a brittle material. Similarly, for a ductile material, let's say aluminum, or let's say very ductile kind of material, gold. So what will happen is you will get a necking formation, and the material will break like this. So this is ductile, and if you have a less ductile material, so which probably neck portion will be not as long as the other one, so it will look something like this. So you can say that this is less ductile, but not exactly brittle, but this is less ductile. So these things you already know, but then again we will discuss about the elastic deformation here. So as you know, in the stress strain curve, in the earlier stress strain curve, let's say for this ductile material, the elastic part of the stress strain curve is this one, that is the straight line, mostly elastic. We are mostly in these lectures we will focus on only on metals, not on ceramics and polymers. So that's why we are talking about this crystalline kind of metallic materials, and we are showing these probably focus on that type of stress strain curve. So this is a material, let's say your tensile specimen. We are drawing not many atoms, so but just to show you what happened in these cases. So what will happen after you do some tensile test, so the material will elongate, and so that means what will happen, the distance between these atoms and the vertical in the direction, these will increase. If you see the distance here is very less, now it is more, so this will increase. So that's the elastic deformation, and what will happen if you unload it. So this is what you did here is the loading, and if you unload it, the material will take the original shape. So what will happen, this will be original shape, that means the deformation is reversible deformation. So the unloading is giving us the same shape of the original shape, but that is not the case in plastic deformation. Plastic deformation is different. So plastic deformation probably anyways these are different for different materials. So mostly in this part we will in this course we will talk about metals, and then we have ceramics. Ceramics also the plastic deformation mechanism can be different, and mostly, as you know, the ceramics are brittle, by the way, and that will not have plastic deformation, much plastic deformation. This is polymer is different. So I just will go back to the earlier slides of the ductile and brittle material slide. So I probably forgot to tell you that, and I'm sure all of you know that. So the ductile means, what does it means, that fracture stress is higher than the yield strength here. So this is the yield strength, and this is where the fracture happens. We need to this is a fracture strength, and so that means for the ductile material, fracture happens after yielding, after plastic deformation. In this case, brittle material, no yielding, directly fracture. So that is the difference that all of you know that. So now if you come here, so ceramics, this is mostly brittle, and probably there will be very little plastic deformation, but some of the ceramics can show some plastic deformation, and the polymers are deformation mechanism is very different, and it is basically stretching and rotation of molecular bonds. So this is for polymers, but as I told you, we are focusing only on metals now. And then if you talk about metals, so we can have a classification of the mechanisms. So we are talking about the mechanisms of plastic deformation here. Mechanisms. The first one is slip, second one is twinning, and the third one is martensitic transformation. So slip is very popular, as you know. So we sometimes call it as dislocation slip, because this involves movement of dislocations, and most metals deform by plastically deform by this mechanism. But another mechanism is twinning, less common, and martensitic transformation is even not all materials will show this kind of transformation. So dislocation to slip is the common mechanism. So we will discuss more on this, and then we will discuss the other two, the twinning and martensitic transformation, also a little bit. So we will talk about crystal defects now. So the crystal defects are can be classified into some categories. This also you studied in your probably in your material science class. So the point defects, which are called zero dimensional defect, and then line defects, which are called 1D defect, and then surface defect, surface or actually interface defects, these are called also called 2D defects, and then volume defects. These are 3-dimensional defects. So point defects are vacancy, impurity atoms, and Frenkel defect, and Schottky defect. These two are for ionic materials, and then line defect, as you know, very popular among metallosis. This is dislocations, and then for surface defects, that can be grain boundaries, twin boundaries, and then stacking fault, and volume defects that can be precipitates, inclusions, voids. Better we should call them a micro voids. Why we are calling them a micro void? Because another void is crystallographic voids, which is in the angstrom level in between the atoms, that is the interstitial sites, and then another one is micro cracks. That means not big cracks, micro cracks. So in the atomic level, that crack is in the atomic level. So this is the mostly we are covering most of the defects here. This is the classification of defects. You can classify in terms of 1D, 2D or 0-dimensional defect. So this figure is from Mark Meyer's book, 13.7 figure number, probably that is should be the same for all the books, and that is the one edition on 1994. So now there are three these kind of figures, and I found it very interesting. So what is happening here is it shows different kind of defects in the same figure. So this one is, these are all atoms, as you can understand. This is an interstitial impurity, interstitial sites are in between the regular lattice sites, and this another one is again one impurity that is called substitutional. Substitutional means that atom is different. Let's say the all other atoms are aluminum, and let's say one atom is copper atom, so that's why it is called substitutional impurity. There can be lot of high number of impurities, but we are showing only one for each. And then this is an extra half plane we call, that is the dislocation. Actually dislocations is, if you see in the perpendicular line perpendicular to the plane of this slide, so that will be called as dislocation. This is an actually edge dislocation. So that this is called extra half plane, whatever I have drawn here. The dislocation line will be on this whatever I am drawing now, and that will be perpendicular to the plane of this slide. That means you imagine in 3 dimension what we were showing in only 2 dimension. And then there is one vacancy here. This is the vacancy, there is no atom here, so that is why it is called a vacancy. And then this part, if you can see, there is some boundaries here. These are atoms are not arranged properly, so this is a small angle grain boundary, small angle boundary. That means actually the grain boundary, if you have one more grain in this direction. So this is another, and this is one grain, let's say. So now we can show some this is although not so clear, you can refer to the book diagram. So there is a twinning also showing here. Twinning will show in another slide as well. So twinning, that's not very easy to find from here. Probably better this twin boundary I am not discussing in this slide, so we will discuss that. We are discussing about these crystal defects. So this is the slide summarizes some of the 3-dimensional crystal defects. So this one is precipitate. Mostly the size is in a nanometer level. So and they are, this is mostly nano sized particles. So they are the primary strengthening agent in many alloys. We will discuss about that. And suppose the precipitates are some compounds, like for aluminum alloys, let's say these are the precipitate, let's say CuAl2 or Cu2Al. Similarly for nickel alloys, the precipitate is Ni3Al. So these are also, what you can see is the dark color are also atoms, although it shows in a different size of atoms, but just to show you this structure. So this is the precipitate, as I told, it's in general it's a nanometer level, or it can be spherical, or it can be plate shaped, or it can be rod shaped. So that is in between the parent matrix. So we call this part as matrix. So if it is, let's say if it is aluminum alloy, so the matrix will be aluminum, and let's say the precipitate will be Cu2Al or something like that. So now the big particle, that's a bigger particle which is in mostly in, let's say, micron level. So this is called inclusion. So inclusions are mostly they are non-metallic oxides, carbides, and sulfides. So these inclusions are very different than the precipitates, and also we have some other defects. So this one is a micro crack. So there is some vacant space here. So, this is a micro crack, it's very small crack. These micro cracks generally do not grow very big, you know. It always in a material there are a good number of micro crack can exist, but the material failure generally does not happen from an individual micro crack. And similarly, there are voids, that is mostly we call micro voids. So, these are, as you know, for ductile material the failure depends on these voids or micro voids. So, there are many voids. So, individual voids are also grow during deformation, during plastic deformation, and also the many voids will come together and join to each other, that is called void. First nucleates and then it grow and then it comes together, that is called coalescence. So, that way the ductile material fails. So, I just will write that is related to ductile fracture, that means the voids are responsible for ductile fracture or ductile failure of or failure of ductile material. So, these are some 3-dimensional crystal defects, and then this is again some defects. Let us say this is a different material and this is another material. So, this portion where the atoms are not very arranged in a periodic order, some of these are some irregularity you can see. So, this is called phase boundary, because let us say this one is phase 1 and this one is phase 2, they are different materials. So, this is the phase boundary, and similarly there is 2 grains here actually. So, this is in a phase 1 we have 2 grains. So, let us say grain 1 and then the second is grain 2. So, now this portion which does not have a very regular arrangement of atom. So, this is called a grain boundary. Grain boundary is also a crystal defect, as we have discussed, this is a 2-dimensional crystal defect. So, similarly we have a vacancy zone. So, this is a group of vacancy or we can call zone of vacancy. So, as I already told, these 3 figures, these 2 slides and the earlier slide. So, these are from the Mark Meyer's book, that is figure number 13.7, zone of vacancy, and similarly there are some foreign atoms they group together. So, that is we can call zone of foreign atoms, zone of foreign atoms. So, these are some defects we discussed, and another 2-dimensional defects. So, that is called stacking fault, we did not include in the earlier figures schematics. So, the stacking fault is maybe a little difficult to understand. So, let us say we are seeing here an FCC lattice and a side view. FCC, as you know, face centered cubic. This is, let us say, a side view. Why we are calling a side view is that that you probably I am sure that you studied. We do not have much time to describe all those about the packings, how they are packed in FCC and HCP. So, it is a little difficult now to summarize it in a very less time, but you just please study these about this stacking fault. So, the FCC packing, that means these are all atomic planes that you can understand. This is one atomic plane which is called as B, and this is C, this is A. So, for FCC the packing order is like that, ABC, ABC, ABC. For hexagonal closed pack the packing order is like AB, AB, AB. So, they are quite similar, AB planes are there, but C is missing here. So, now if you are talking about a FCC lattice, this is the perfect lattice without any defect, perfect FCC lattice. But sometimes what happen, sometimes there will be some defect. So, there will be some missing, let us say here we have a plane missing here, we are getting only AB picking, there is no C plane. So, that is where the fall is, and that is called stacking fault. So, in summary, so stacking fault is the fault in the stacking sequence of a material, like for these crystalline material. So, you can check this basics from a material science textbook. So, and the stacking fault has stacking fault energy, I will just write as Fe, that means E means energy. So, this stacking fault energy, all the crystal defects, not only stacking fault, but the dislocations and other grain boundaries, twin boundaries, they have energy associated with it. So, like perfect crystal may be at the minimum energy level, but these defects will increase the energy. So, this stacking fault energy is related to mechanical twinning. If the stacking fault energy is high, twinning, the chance of twinning is less. So, I would like less twin formation. Like aluminum has a high stacking fault energy, and that is why it does not undergo much twin deformation. So, we will talk about this plastic deformation by shear. So, what we are doing is there are two rows of atoms. So, if we apply some shear stress like this, let us say tau is the shear stress. So, just we are trying to shift these let us say plane of atom this way and the other plane in this way. So, what happened, the result is this one. So, now while doing this, so the maximum shear stress tau m, that at which the slip will occur. So, that will be equal to Z twice pi, Z is the shear modulus and B by A. So, if B equal to A, we can assume B equal to A, oh sorry, I did not even tell you what is B, sorry about that. So, B is nothing but the distance between two atoms in a plane, and what is A? A is the distance between these two planes, so interatomic distance. Okay. So, if B is equal to A, if it is not exactly equal also, this will be in the is of the same order. So, that is why we are assuming B is almost equal to A. So, that will give us tau m, the maximum shear stress at which the slip will occur, is equal to G by twice pi. As you know, the shear modulus is in gigapascal. So, for most metals this value will come like 3 to 30 gigapascal. So, this is a very high value, that much shear stress is required. So, that is possible for a perfect lattice without any defect. Defect here mostly we will be discussing here now dislocations. So, if it is a perfect lattice, let us say without any dislocations or even other defects, dislocations and other defects. So, its strength will be, this is the shear strength actually, the shear strength will be very high. So, this is theoretical shear strength. So, theoretical strength is much higher than what we get in experiments. So, that will be much higher, let us say it is 100 times or thousands times higher real strength of the material. The real strength you can determine from experiment. So, why this is happening? So, this happens mostly because of the dislocations. So, that means dislocations make the crystal weak, make the material weak. So, dislocations mostly, as I told you, this dislocation is mostly for crystalline materials or metallic materials, or we can call these metals and alloys. So, now we will see what are these dislocations. Dislocations are line defects. So, there are different types of dislocations. So, first one is we call edge dislocations. I am sure all of you have read that, but just for your review, and I am doing this. There is another one called screw dislocations, and the third one is called mixed dislocation, which is in between these two screw and edge. So, first whatever we are drawing here is a edge dislocation, and the second one is a screw dislocation. This is screw dislocation. I would write here, this is edge and this is screw dislocation. We did not we do not have a mixed dislocation here. So, what is happening here is the slip happens in this direction, and the extra half plane, that means an extra plane of atom, will move in this direction. For the dislocation, this you can see that this part is just moved from this side, from left to right, that you can, I am sure you can understand this. So, this part of the material is shifted, so shear is shearing in this direction. So, when you call Burger's vector, which is the shortest, we call lattice translation vector. Lattice translation vector, that means from one lattice point to other lattice point, shortest lattice translation vector. So, that is, this is the B here. So, B in this direction is this one, and then here the B direction is this one, that is the slip directions in both the cases. And our dislocation line in this case, and for edge dislocation, this is the dislocation line. I will just write maybe L for dislocation line vector. This is the dislocation line, and in this case in screw dislocations, so this dislocation line is this one. So, that is why we say that in edge dislocation the Burger's vector is perpendicular to L, the dislocation line, here you can see, and for screw dislocation the Burger vector is parallel to dislocation line. You can see that the Burger's vector direction and the dislocation line direction is the same, and these two figures on the right hand side shows the result of these deformation. So, after this deformation you can get a step created here. So, we will see now see about these edge dislocations. So, here we can see that there is an extra half plane here, the other lines of atoms are you can see that if you are going away from this. So, you have a one full plane of atom, but here in this case you have a extra half plane of atom. So, that is actually dislocation, and the slip direction of the Burger's vector direction in this way, and the L direction, that the dislocation line direction is along at this point, and the perpendicular to the plane of the slide. So, that is the dislocation line. And so, if you see after some time when you are shearing the material, so you are exerting some shear force, so the extra half plane will shift one atomic distance towards the right, and similarly here if you shift more, if you are exerting more shearing force, so then the extra half plane will go towards more right, and then at last it will be just will be out of the
this crystal. So now what will happen, there will be a step formation, sorry, here we have probably one more atom. So there will be a step formation. So now the entire body, let us say we are having showing only a few atoms, but the entire body will look like this. So what happened here, again I am repeating this. So extra half plane was here in this case in the first step, and in the second step it has a little displacement of these extra half plane, and then again this is the displacement, and then again in the third case this is the third step. So what will happen, what happened, and this is again one step towards the right, and in the fourth case again one step towards right. So now this dislocation comes out of the crystal, so that creating a step we call it a small step. So this is very at the atomic level it is very small, so it is in the angstrom level. But if lot of dislocations, like thousands of dislocations come out, and then what will happen is this step will grow bigger, and then you can see some plastic deformation. So the plastic deformation will be, then we can see with our naked eye. So if lot of dislocations, hundreds of thousands of dislocations come out and make a step like this, make a big step on the surface. So I will just let you know what is slip systems. The slip systems are nothing but a combination of slip plane and slip direction. So what is happening here is the black lines show the unit cell. So unit cell means, let us say it is a FCC FCC lattice, and we have atoms at the corners, and then we have atoms at the surface the face center as well. It is something like this, the face center as well. So now what will happen is this plane, the blue line, this plane we call it the 111 plane. So considering this as the origin, okay. So so similarly for FCC material, we are talking about FCC material here, FCC slip systems. So 111 plane, and we write actually the curly bracket because this is a family of plane, and similarly family of directions is 110. In this case, if you take this direction, and or if you take this direction on the plane, and or if you take even this direction on that triangular plane, that is 111, you can take 3 directions which are like 110 directions. So now the combination of this 111, 110, so that means why I am saying as a family, if it is a single slip direction we write it like this. So why we call that a family, because they are a combination of planes and combination of directions on which so the dislocation moves. So dislocations moves on slip planes and in slip directions, okay. So this let us say the family of plane means it may be 111 or 1 minus 11, or let us say minus 111 or something like that. So that is why it is a family of plane. So these are the particular planes and directions, that is crystallographic directions and crystallographic plane where the dislocation moves, that slip happens, that is the basis of plastic deformation. Now again coming to the same dislocation movement. So if you have a, let us say, material and we are exerting a force, and let us say the normal stress sigma, tensile stress, and if your slip plane is in direction, in this is the slip plane in the material. Let us say we are assuming a single crystal here, not very complex multiple crystals or polycrystalline material. So within the single crystal, so let us say this is we are FCC, and this is a 111 plane, and let us say this is the slip direction which is 110 direction. So now what we need to do is we will resolve this sigma along this plane or along on this plane along this direction, that is this tau. So, we will resolve this tau, we will calculate this tau, that is called resolved shear stress. So, we resolve that and calculate that stress from our sigma. Okay. So, if you know these angles theta, the angle what is made by these direction phi, so then you can find out this tau, resolved shear stress tau, and if resolved shear stress is greater than a critical value, I will write tau critical, then the slip will happen. Then slip happens, that means the dislocation moves. Below that or we just write greater than equal to. So, below that tau, if it is below tau critical, so slip, no slip, or we can write no slip. So, that is why this tau critical is called critical resolved shear stress, so that is material dependent. So, it is a material property, critical resolved shear stress. We will now talk about mechanical twinning. As I told you that twinning is also a plastic deformation mechanism. Here on the left hand side we are showing you slip, that means dislocation slip, and on the right hand side we are showing twinning, mechanical twinning. So, slip, as I told you, these are some slip planes where these are the planes, let us say where the slip happens, and ultimately we are getting a deformed shape like this. So, this shape, deformed shape, is formed because of the many dislocations go out of the crystal and form these steps. So, now what happens in a twinning is, so you can see that these atoms are aligned, and suddenly when you are deforming the material, so the alignment of this portion will be different. Suddenly it change the orientation. So, now generally we in twinning we call that this is a twin boundary. So, that means a twin boundary formed in between a twin region. So, this is twinned and this is untwinned, not twinned. So, this happens during plastic deformation. As I told you, not all material will undergo probably twinning, and this basically is a across the twinning plane, these atoms are like has some symmetry, reflectional symmetry, that means mirror image of the one side will be the other side of the twin boundary will be the mirror image, that is called reflectional symmetry. So, this is one way of plastic deformation, but it is less common than dislocation slip. So, we have already discussed about two plastic deformation mechanisms, dislocation slip and mechanical twinning, and the third one is martensitic transformation, martensitic phase transformation. So, some of the alloys like for example nitinol is one example, which is nickel titanium alloy. So, this nitinol or some other materials, so they undergo some crystal structure changes and during their plastic deformation. So, here so this material is in austenitic form, and then when we cool it during after cooling, so it will form martensite. So, if we deform this martensite, after deformation it will come to a different structure. It is martensite, but it will have a different atomic arrangement, and then if you again heat again, it will go to their original austenitic structure. So, these kind of alloys some of these kind of alloys are called shape memory alloys, because when you cool the material and you deformed it and again you heat it, you get the original shape. So what it can does is it can remember its shape, Suppose if you have a let's say wire or thin a bar of that material, and you are bending the material like this, bending the bar like this, and so what if you hit it, then the bar will come to its original shape. So that means the bar remembers its shape and then it goes back to its original shape. So that is you can study about shape memory alloy. I am sure most of you know about shape memory alloy, but this is one of the plastic deformation mechanism. So the deformation is associated with the structure, crystal structure changes. So we are not going to discuss details about this, but you can study in any material science textbook regarding this matter-static transformation. So now we will talk about the strengthening mechanisms of metals. So we, for our applications, what we want to do is we want to strengthen our metal if it is not sufficiently strong. So for that purpose, strengthening means we want to restrict the plastic deformation so that we can exert higher load. So for that reason, what we can do is in a earlier slide, so what we found is the dislocations, which is one type of crystal defects. Dislocations weaken the crystal or the material, the crystalline material or metallic material. So now, as we discussed, that if you have a perfect crystal without any dislocations, so you will the strength of the material will be much higher than the crystal with a without dislocations. So to strengthen the material, what we can do is first we can try to remove the dislocations, remove all the dislocations, so that we get a theoretical strength. That is, by the way, not possible. It's actually it can be possible, but it is very difficult. There you can probably make very small we call whiskers, very small particles which may have the perfect crystal without any dislocations. But anyways, if you deform more, the more dislocation will generate. So dislocations will generate. Even if you are starting with a perfect crystal, dislocations will generate, and there are mechanisms to generate dislocations like Frank-Reed source. You can study these if you are interested, like Frank-Reed source of dislocation generation. I am sure some of you already know about this. So to remove all the dislocations for a bigger sample, it is impossible. For small whiskers, it can be possible, but again dislocation generates with deformation. So we are not going to use this technique, or it is almost not possible. So there can be another technique now to strengthen the material, to create resistance to dislocation motion. So why we are saying that we are if we want to strengthen the material, we need to work on dislocations, because the plastic deformation is mostly controlled by dislocation movement. If it is not mechanical tuning or matter-static transformation, so most of the plastic deformation depends on dislocation movement. So if we can restrict the movement of dislocations, then we can restrict the plastic deformation, and that means we are strengthening the material. So, we will now see how to create resistance to dislocation motion. There are different ways to do that, so that we will discuss one by one. Let us say first one is strain hardening, or we call it as a work hardening. And the second one is solid solution strengthening, or you can use the hardening and strengthening word actually interchangeably. This is what we are talking about metals, this crystalline materials. So, and another one is the grain boundary strengthening. And then precipitate strengthening, and dispersion strengthening. So, we will now discuss one by one.
Oh, sorry, this is I should have wrote difficult. Actually, initially I thought I would write not possible, but this should be only difficult. It's not not difficult. So basically, the remove all the dislocations is possible, but it is very difficult.
So, what is strain hardening? So, you can see some cars here. So, this is just to represent the strain hardening. So, what happens during strain hardening? So, as you know, during the plastic deformation, let us say this is engineering stress strain curve. So, this part is of this curve is we call as a strain hardening. So, what happens in this portion? So, with strain, with deformation, so dislocation density will increase. Dislocation density increases with deformation or with strain. So, what happens if the dislocation density increases? It's something like this. This is like a traffic jam kind of situation. Traffic jam. So, here in this case, in the earlier case, less traffic. So, this is actually the dislocations movement can be compared to a traffic movement, vehicle movement on a road. So, here in the first case, the less traffic, and so it is very easier for the cars to move. So, and but here in this case, it's not very easy in a traffic jam kind of situation. It's not very easy to move. So, similarly, when you strain more and more, so dislocation density will increase because of the dislocation generation, like what we call one of the generation mechanism is Frank Reed source. So, dislocation will generate and dislocation density will increase. So, this means dislocation increase of dislocation means a traffic jam kind of situation. Traffic jam kind of situation. So, that will that means the plastic deformation is difficult. Plastic deformation is difficult, more difficult, and that means that the strength increases. Strength increases. So, there is a relation, it is an empirical relation for shear stress required to move a dislocation. So, that looks like this. So, where this rho is the dislocation density, rho is the dislocation density, this is shear stress required to move a dislocation, move one dislocation. So, I will make a boundary here. So, this rho is the dislocation density and A is a constant, and then tau naught is the base stress to move a dislocation in the crystal in the absence of other dislocations. If there is no other dislocations, so tau naught is required. So this is the, you can check this relationship in a materials book. This is base stress when there is no other dislocations or no other interaction with other dislocations. So this is what we are showing is here, it depends, the shear stress required depends on the dislocation density. So if rho increases, then tau will also increase. So that's what this relation says. So that's an empirical relation. So now we'll go to solid solution strengthening. As you know, let's say we have a edge dislocation here, and if you see there are no planes on the below. So here actually the slip plane is this plane perpendicular to the plane of the slide. So and again this is a solute atom. So what will happen now? So there will be some some stress field around this dislocation. Let's say in this region will be in compression, I will write C for compression, and this region will experience some tensile stress, I will write T for tensile. And similarly due to this solute atom, there can be some stress field that can be compressive or tensile depending on the solute atom. If it is a, let's say, smaller solute atom, then it can be probably even tensile stress field, or if it is a bigger solute atom, it can be compressive stress field. So depending on that, there will be some stress field. So if a dislocation approaches a solute atom or a group of atoms, solute atom, so what will happen? It will get some resistance. So this resistance will increase the difficulty of dislocation movement, and that will increase the strength of the material. So this is called solid solution strengthening. I hope most of you know that what is solid solution. Please refer to a standard material textbook like probably Callister. So I am just writing the Callister's book is good, or otherwise you can go a classic book on mechanical metallurgy, Z.E. Dieter. So mechanical metallurgy book. So and I think W.D. Callister. These are the books probably you referred in your basic material science course. So the next one is grain boundary strengthening. So we are now discussing about different strengthening mechanisms. So this is the third strengthening mechanism we are discussing. So here we have a edge dislocations. If you see, these are other planes of atoms. So here we have a edge dislocation. So this is our extra half plane, and so this is our slip plane. The dashed line is our slip plane. So what happens is, this is the grain boundary. As you can see that this is, I will write GB for grain boundary, and as you can understand that the orientation of these atoms are different than the other grain. So this is grain number, so this is grain 1 and this is grain 2. So what happens when the dislocation during the deformation, let's say we are exerting some shear stress and these extra half plane is moving towards right, towards the grain boundary. So what will happen is when it tries to cross the grain boundary, it will get some difficulty because the slip plane is oriented in a different direction. So that's why what will happen is the dislocations will we call pile up at the grain boundary. So dislocations will pile up like our vehicle pile up, that you can sometimes when some accident happens with several vehicles, generally we call them pile up. So that vehicle pile up at grain boundary, and that means there is a resistance to plastic deformation. That means there is a resistance to plastic deformation. That means that the strength will increase. strength of the material will increase. So, dislocation movement restricted, and that means the plastic deformation is restricted. So, the another one is precipitate strengthening. So, as you know, precipitates are small particles. I discussed earlier also. Let us say this is one particle, this is not very clear here, but it is a spherical particle, and we are having these as a extra half plane. Please try to understand this from the earlier figure. So, here somewhere I showed you, here I showed you this one is the extra half plane in two dimensional case, and I told you this horizontal line is the slip plane, and here we are discussing in a three dimensional case, but without any atoms. So, atoms are like, let us say the atoms will be here, but we are not showing the atoms. So, this is the extra half plane, that means a plane under that is missing. So, this plane is missing, under that it is missing plane. So, that is why it is called extra half plane. And now this one is the slip plane, because the dislocation will move on the slip plane. This is the dislocation line, and this dislocation line will move from left to right. Let us say it is because of some shear stress. This is, let us say, we are exerting some shear stress, and the dislocation line is moving from left to right. Now, there is an obstacle. This is the precipitate. So, what happens, the precipitate is a small particle, mostly generally the precipitates are nano sized particle, but that they are probably intermetallics. As I told you, for a let us say aluminum alloy, the precipitate can be Cu2Al. So, the structure is different, the crystal structure is different. Sometimes that can be of same crystal structure. Let us say aluminum is also FCC, and this precipitate may also be FCC. Sometimes the precipitate may be BCC or hexagonal closed pack. So, what will happen is this dislocation line will face some difficulty to cross this precipitate. So, what will happen, this is the dislocation line, again we are showing from two dimensional view. From this side, the side view we are showing here, this is the slip plane, and the dislocation is going this way. So, this is the extra half plane actually, dislocation line will be perpendicular to that. So, this is the precipitate. So, after some time what will happen, this extra half plane will cross, and the precipitate will be sheared. This is called shearing of precipitate. So, during this shearing there are two results. So, one is that is surface area of the precipitates increases, and also the force required for the dislocation line to cross the precipitate, actually it increases. So, there are more force required. So, that is why this strengthening happens due to precipitate. But these are the precipitate which are we call coherent precipitate. Coherent, you please check it what is coherent and incoherent. So, just to very simple language, the coherent precipitate are easier to cross for these dislocations, but there can be some incoherent particles, and this is now we are coming to dispersion strengthening. These are some particles that can be some incoherent, probably I told you inherent, that should be incoherent. So, this incoherent particles, that can be some inclusions or some dispersed particles, or some can be incoherent precipitate. So, this line is the dislocation line. So, dislocation lines here is trying to move towards the right side, and then what will happen, because these precipitates are incoherent, that means this is difficult to cross or difficult to cut through or shear through, then it will form like this, and finally it will try to form a loop, and finally it will form a loop around the precipitate or whatever particle it is, and that is incoherent particle, and then dislocation line will again move. So what happens, dislocation lines circles around these precipitates, and then again it will be a new straight line, straight dislocation line will be move towards right, crossing that. So subsequent dislocation line, if you think that there will be one more dislocation line behind this which is also traveling in the right side direction, then there can be one more circle around it, and these circles or loops, the dislocation loops are called OR1 loop, or it is sometimes called as OR1 bowing mechanism. It's like it's make a bow like shape, especially here you can see this is a bow like shape. So this is called OR1 bowing mechanism.
Sorry, this incoherent is not kind of a separate word separated by a dash. So incoherent, this is the correct word. And also when I told about the bowing mechanism, so I told that this is the bow, but generally bowing, I mean bow shape, although this is also a bow shape, but generally here the bowing means simply shape like this. So don't confuse with that. So simply I mean when you have a particle and then simply the dislocation line takes a shape like this, so that is we call bowing, not exactly this type of bow shape. So generally we sometimes imagine the bow like that, but even this is also a bow. This is also a bow. So both these shapes are bow shape, but don't confuse that there are two arcs needed for a bow. Only single arc is also enough for to call it as a bowing mechanism.
These are the strengthening mechanism of metals. So just I want to tell you one more thing that I forgot here in the grain boundary strengthening. The grain boundary strengthening also one mathematical relations that is called Hall-Petz relation. With the help of that relation we can show that quantify the grain boundary strengthening, that is sigma y equal to sigma I plus k root d. So d is the grain diameter here. So grain diameter, and k is a constant, and then sigma I is also a kind of the base stress we discussed earlier. So that is the stress to move a dislocation in a single crystal, sigma I, and the sigma y is the yield stress. So yield stress will decrease if we have a bigger grain. That means if the grain diameter, so if d is higher, that means sigma y will be lower. So for that reason, so if you have a fine grain structure, fine grains means smaller grain structure, the material will have higher strength. So material will have higher strength. So you can probably understand that if it is fine grain, there is more grain boundary, more means the length of the grain boundary will be more, or we should not call it a length, because what we are seeing here, the grain boundary is in two dimensional, that is in three dimensional surface. So the more grain boundary area, so that's why more resistance to dislocation movement. So that's why the strength increases. We actually completed this lecture on material science basics. So this is I was quite fast in this lecture. I was not going in a pace like what we followed in earlier lectures, because I believe most of you already learned these concepts of material science in your basic materials courses, probably in your second or third year of your bachelor's degree. So I think these are the mostly the basics we are using, or we will be using in our dynamic behavior materials course, but there can be some more concepts we may require. So in during our subsequent lectures we will try to discuss very briefly about those concepts. After these, so we will talk about the phase transformations that is induced by shock wave. So that's all for today. Thank you.